Hello, welcome back. Today we're going to go over graphing equations. I'm going to mainly take you through linear equations, but we'll do some inequalities as well. And if we still have time, we'll do some systems of equations and inequalities in this video. So first thing I want to review is just plotting points. Remember, going back to your high school courses, the x-axis here on the Cartesian plane is the horizontal axis, the vertical axis is your y-axis. And anytime you plot a point, it's listed as x comma y here. So you're going to graph the x first and then your y. This location is called the origin, where the two axes meet. To the right of the y-axis, going this way, is positive x values. To the left is negative x values, just like you'd see on a number line. Likewise, going vertically above the x-axis are positive y values, and below are negative y values. So if we're going to plot the point 3, 4, you can start right here at 0, 0 and go to the right 3 and then up 4. And so this has an xy coordinate of 3, 4. And that we can label points using capital letters. So that is point A there. Negative 2, 4 would be the x value is negative and the y value is positive there. So here is negative 2, 4. Negative 5, 1 means the x value is a negative 5, and then the y value is negative 1. So here, 1, 2, 3, 4, 5, good. And then 7, negative 8 would be an x value that is positive 7, but the y value is negative 8. So down there. So, and then you can go through and write those points if you want to in, or you can't really drag them over because you're not on a computer like I am. And there's your basics to plotting points. That should be just a quick review, but if you need more practice on any of this stuff, make sure that you always say something to me and we'll get you caught up. Now, the slope between 2 points, go ahead and try graphing these 2 points. So we have 5, 7. Oops, my marker's out. 5, 7 right there, and negative 3, negative 2 right there. And what I mean by the slope is I want to know the steepness between those two slopes, between those 2 points. Or in other words, what is the rate of change between those two? So if I drew a line between the two, how steep is that line? How can we describe the steepness of it? So typically, we say it's a rate of change. So for every 1 I go over on the x-axis, how much do I go over up or down on the y-axis? And we can take this by the difference between your x and your y values. So if we were to make a triangle here, it would look like this. And if we were describing how much did I change in my x, it went from negative 3 to 5. So how much to the right did I go? Well, you can say 5 minus wherever you started, the negative 3 there. And this gives me 5 plus 3, which is 8. So this side of the triangle is 8. And to figure out how much I rose over that period of run, we could say 7 minus a negative 2, which becomes 9. So we rose 9, we ran 8. And so we can describe our slope as being 9/8. Slope is your rise over your run. So that's how much we rose up, that's how much we ran between those two. And typically we write this out in equation form like this. We say y2 minus y1 over x2 minus x1. That is what we call our slope, usually also described as a lowercase m. So that's exactly what I did right here. I chose one of these points and I said, let's call this x2, y2. And this point I called it x1, y1. And I put it into this equation right here. Now, moving further, when we talk about linear equations, well, linear equations are equations of lines. That's why you have that word line in right there. And what we mean by a line in mathematics is there is no curve to it. Like this right here is not considered a line in math. You might say, oh, you drew a curvy line in everyday language, But when we say a line in math, we're saying there is no curvature to it. It's straight, like that. That is a line. And the slope here is a constant. Okay, notice the slope here might change. Can't really describe it, the steepness, as the same here as it is maybe right here. So when we discuss linear equations, we are making the assumption there that it is a straight line. So this is an equation of a line. And before we get into what the parts are, I want you to try out some test points in this equation here. So let's put in the following numbers: -3, -2, -1, 0, and 1, 2, 3. So put in -3 right here and see what y becomes. So 3 times -3 is -9. -9 plus 2 is -7. Put in -2. You get -6 plus 4, which gives you -4. So finish that out. You should get -1, +2, +5, +8, and +11. And graph those points. So for the first one, graph -3, -7. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. And graph the rest of them. So that's what the rest of them look like when they're graphed out. And notice we're starting to form a line here. The inputs here do not have to be whole numbers. We could do integers. We could do something like 1/2. So let's go and graph that point 1/2. If you put in 1/2, you end up with 1/2 times 3, which is 1.5. And 1.5 plus 2 is 3.5. So at 1/2, you're at 3.5, or 3.5. So look here, at 1/2, we're at 1, 2, 3.5. And notice as we add more and more points, this thing is going to form a line. So our line goes through just like this. A little bit off, I'll drag it through like this. So they all end up on this line right here. Now, this is just the introductory way that we start to graph lines, by taking an equation, putting in points, and plotting those points. If it's a linear equation, it should line up like it is. If it's not, it'll be some type of curve. But when it's in this format, there's a faster way to do it than plotting points. And so a couple things to note here. Where does it cross the y-axis? What's the y value? It crosses right here at the point 0, 2. We call this our y-intercept. The y-intercept is where it crosses the y-axis, and then later on you might discuss the x-intercept is where it crosses the x-axis. But for right now, we're just concerned about the y-intercept, and it crosses at 2. Then notice how much each one goes up here. For every 1 that I add here, plus 1, plus, well, going from here to here is plus 1. Notice your y value increases by 3. So for every 1 unit I go up on the x, I go up 3 on the y. That is your slope. That's your rate of change. So notice if you're to write this out as your difference in y's over difference in x's, and calculate that, you would get 3 over 1, or just 3. So our slope is 3. So that's where we start to see some patterns in here. We got 3 for our slope. We got 2 for our y-intercept, and notice those numbers are present right here. So much that we can actually graph this using an easier format, and you might have learned this in algebra, where y is equal to mx plus b. This is our slope, and this is our y-intercept, and we call this slope-intercept form of a linear equation. So when the y is by itself and you have a coefficient for the x and some type of constant being added or subtracted at the end, it is in slope-intercept form. So I already know that my slope is 3 and my y-intercept is 2. To graph a line, any line, if you give me 1 point in the slope of the line, I can graph the whole line. So right here is the point, and right here is the slope. I know the y-axis, the y-intercept is where it crosses the y-axis. So they're giving me that the y-intercept is 2. So it crosses at 2. There's your point on the line. they're telling me the slope is 3. So make 3, it's not a fraction right now, make it a fraction if it's not. The slope is 3 over 1. So it tells me to go up 3 and over 1. Whenever the slope is positive, this graph should look like it's going uphill left to right. So up 3 over 1, or you could go to the left by going down 3 and to the left 1. And then connecting your dots will give you your line there. So that's an easier way to graph it versus plotting a bunch of points, is using that slope-intercept form. Try this one out. Try graphing it without plotting points. Pause the video. All right, so if you pause the video, first thing you start off with is your point. That's your y-intercept. It's at -5. So I'm going to go down 1, 2, 3, 4, 5. And this right here is my slope. Include that negative with it. So you can write it like this, -1 over 3. And if the slope is negative, it should be going downhill like this from left to right. So I'm going to go down 1 and to the right 3. Or if you wrote out your slope, when you write this out as a fraction like this, that works too. Go up 1 and to the left 3. Up 1 to the left 3, or down 1 over here to the right 3. And then connect your dots to make your line. Put arrows on the end to show it goes on forever. And so there's your line. The y-intercept's -5, the slope is -1/3. Try this one out. So this one says that the y-intercept right here is 3, so we're going to go up 3, put a dot. And it says the slope, notice there's no coefficient that we can see right here, and we talked about that before, that's just a 1 in front of it. So the slope is 1 over 1. And so rising 1 and running 1, or falling 1 and going to the left 1, you're going to get a line that looks like this. Once again, put some arrows on the end to show it goes on forever. Just double check, always double check, is the slope positive? Yes. And is it going uphill left or right? It is. So that checks out. Try this one out. So this one, it's pretty easy to see the slope. The slope's right here, 3/5. So we know we're going to be rising 3 and running 5, and it's positive. But I don't see a y-intercept on the end right here. This is the same thing as saying plus what? Plus 0. So we don't always write the plus 0 there when it's a plus 0. That just means that the y-intercept is right here. And then from there, we're going to rise 3 and run 5. Or fall 3 and run 5 this way. And then connect your dots. Now, just to check, is it a positive slope? Yes, and yes, it's going uphill left to right. Doesn't mean you'll get it right just because that matches up. Sometimes I see students will graph everything right except for their line will be going that way. And if they did that double check where they said the slope's positive, but this is showing a negative slope, they would realize, oh, wait a minute, I did something wrong. So it saves them a few points there in the grading. Try out this one. So this one says y equals 4. There's no x there at all. So how could we write this in y equals mx plus b? Well, the b is 4. That's your constant. What would make x disappear? What would m have to be for x to go away? M would have to be 0. And so notice if you have 0 times x, it's just 0. And 0 plus 4 gives you just 4. So that's what happened here. The slope is 0, which means it's a horizontal line. There is no rise forever how much you run. So in this case, we're going to go up to 4. That's your y-intercept. And then you rise none and run whatever you want. And this becomes your line. Now another way I like to look at this is saying y must be 4. And since there's no x, x can be anything at once. So if you pick any point on this line right here drawn, and I ask you to tell me what is the point right here, you would say that's at x value of 10 and a y value of 4. Right here, The x value is 0, the y value is 4. Right here, x is -1, y is 4. Right here, x is -7, y value is 4. No matter what the x value is, y must be 4. So there's no bound on x. X can be whatever it wants, but the y value must be 4. That's a similar thing when we see something like this, 3 equals x. Now, in this case, this is not slope-intercept form. All right, so it's not in the y equals mx plus b format, but it's still the equation of a line. So we're going to treat it the same way I did here at the end, where I said if we look at this as x has no bound but y must be 4, here y has no bound. Y can be whatever it wants, but the x value you're plotting must be the value of 3. So what would that line look like? Well, let's say y were 0. If y is 0, what must x be? 3. What about if y were 1? What must x be? 3. What if y was -5? What must x be? 3. This is saying x must be 3, but y can be whatever it wants to be. So when x is 3, y is 0. When x is 3, y can be 1. When x is 3, y can be -5. And we can keep doing this. This is the equation of a vertical line at x equals 3. Okay? We put the arrows on the end to show it goes on forever. So when it's a horizontal line, it's y equals something like this. Put those arrows on. When it's a vertical line, it looks like that, x equals something. So try this one out. Try graphing this one. So if you start to look at this and say, that's not in the format y equals mx plus b, well, let's try to make it that way. So get y by itself by doing some solving here. Subtract x from both sides. You get 2y minus 3 equals -x plus 6. Add 3 to both sides. 2y equals -x plus 9. And then divide both sides by 2. So y equals -1/2 x plus 9/2. So I had to, when I divide both sides by 2, I have to divide each one of these by 2. And that gives me what I've got written down here. So this tells me the y-intercept is 9/2, or the same thing as 4.5. So I'll go up 1, 2, 3, 4.5. And then the slope is -1/2. So I drop 1 and run 2. And then connect your dots. Once again, the slope is negative, so it is going downhill left to right, and it's a -1/2, -1/2. And notice each time, because I started out at 4.5, when I go down 1, I'm like at 3.5. When I go down 1 again, I'm at 2.5. When I go down again, I'll be at 1.5. And so that's the way my slope carries it through. Now, there are other ways we can write equations of lines besides slope-intercept. Slope-intercept is the most common in algebra because you're learning about slope and intercepts. We can also see this, and this is called standard form, where it's in the format of ax plus by equals c. And sometimes standard form is helpful because we can quickly figure out what are your intercepts. So for instance, let's first look at some y-intercepts before we look at how to graph this. Let's suppose the y-intercept is 2. At the y-intercept of 2, what is the x value? The x value is 0. What if we had a y-intercept of 9? What's the x value there? It's 0. What if the y-intercept was -3? What's the x value? It's 0. So by this, observation, we're saying that anytime you have a y-intercept, or anywhere the graph crosses the y-axis, your x value is 0. So anytime you give me an equation of a line and you're asking me where's the y-intercept, if I put 0 in for x, I can figure out my y-intercept. Go back and look at this one. Actually, let's look at one that's already in the format for me. If we go back and look at this one right here. Let's suppose I didn't know about y equals mx plus b. With this being the y-intercept. But I do know that when it crosses the y-axis, your x value is 0. I can put 0 in right here for x and figure out the y-intercept. 0 plus 3 is 3, so I know the y-intercept's 3. Or looking at this one. Let's suppose I didn't know that this was in y equals mx plus b format, and I just want to know where does it cross the y-axis. Well, once again, if you put 0 in for x, make this a 0, you get 1/3 times 0 minus 5. This just becomes 0, and I get -5. So I know that when x is 0, y equals -5. So putting 0 into the equation will tell me where the graph crosses the y-axis. So what makes this handy is whenever I put 0 into this thing, this disappears. It just becomes 0. And so now I can just solve this equation for y, and I get y equals 2. So I know that my intercept is going to be right here at 0, 2. Now, let's talk about the x-intercept. The x-intercept is when the graph crosses the x-axis. So if it were to cross right here at 3, the coordinates would be at 3, 0. If it crossed at 0, it would be 0, 0. If it crossed, say, at -10, the coordinates would be -10, 0. If it crossed at +9, it'd be 9, 0. Notice on all of these, the y coordinate is 0. So if I want to find out where does my graph cross the x-axis, I just put 0 in for y. And so let's do that and see what we get here. So if you put 0 in for y right here, that makes 15 times 0, which is just 0. So that gets covered up. Solve this for x, and you get x equals 6. So that means the x-intercept is 6. So 6, 0 is where it crosses there. Notice I've got 2 points there. And when I got 2 points, I can draw a straight line between them. I'm going to try to get that so that it goes through both of them. Oops. And when I draw that line between them, I've got my line there. So this is what we call standard form, and you say, wow, that's way easier. Why don't we always do it like that? Well, these numbers don't always work out to be whole numbers. And so if you got something like a y-intercept that's like 5/8 or something like that, it's hard to graph that accurately. So we don't always use that, but when it is in standard form, sometimes we can recognize it and graph it pretty quickly just by graphing the x and y intercepts. The other way that we graph lines is by doing what we call point-slope form. And this is more popular in my pre-calc and my calculus classes to use point-slope form. And it's kind of like slope-intercept, except for we're not starting off with the y-intercept of an equation. We are going to start off with just any point on the line. So this any point on the line is going to be my x comma, or x sub 1 comma y sub 1. And so notice in the equation, this is where they're written. Here's y sub 1, here's x sub 1. So in this first equation here, where did we put in for x sub 1 to get -5? Well, we must have put in a +5. If you put 5 in this equation, you end up with x minus 5. And what did we put in to get -3 right here? We must have put in a +3 to get -3 right there. And then notice our slope is still hanging out right here. That's our slope. So this, by looking at this equation, I can tell you that some point on the line is going to be at 5, 3. And the slope is 1/3. So I'm going to first graph this point. So we go over 3, 4, 5, and then up 3. That's your starter point. The slope is positive 1/3. So we rise 1, run 3. Or you can say fall 1, run 3 this way, and draw your line through it. So for this one, a lot of students don't like this because they're in Algebra 1, they're taught slope-intercept form so much, but it's really not that much different than slope-intercept form. The only difference is we're not starting with the y-intercept. Instead, we're starting with this point right here. Just remember, you always want to take the opposite sign there. So it says -5, it's going to be at a +5 there. -3, it's going to be at a +3. And then your slope is right here. Try this one out. So for this one, where is our starter point? We're going to take the opposite value here, +1, and the opposite value here, -4. That's our starting point at 1, negative 4. The slope is negative 2/5, so we're going to fall 2 and run 5. Or you can rise 2 and go 5 this way. And then draw your line in between. Now, with all that said, we also have inequalities. So inequality is saying that y is not equal to, but y is either less than, greater than, less than or equal to, or greater than or equal to. So in this case, we've got a y is less than. And our next one, we're going to look at y is greater than, and the bar means or equal to. Could be equal to that as well. So how do we graph something like this? Well, we're going to start off by graphing it like it were an equal sign. So pretend like it's an equal sign and graph this. And so notice this is in y equals mx plus b format, or slope-intercept format. Graph your intercept first. The slope is negative 1/2, so we go down 1 over 2. And then the only thing left here is we're going to change this to an inequality. So the trick here is, if there's a bar underneath, this needs to be a solid line. If there's no bar underneath, it needs to be a dashed line. So we're going to put a dashed line in here. And there should be arrows on both ends. This thing is just set to do arrow on one end. And so this tells me that it's not equal to any point on this line. But we need to also shade a side. So this is a bunch of solutions. Anytime that the y value is less than this side of the equation here, it's going to be a true statement. So pick a point, and I usually pick the point 0, 0 just because it's easy to calculate. So I'm going to put in the point 0, 0 into this equation, and I get, if y is 0, is it less than negative 1/2 times 0 plus 5? Is that a true statement? So we finish it out. Negative 1/2 times 0 is 0, plus 5 gives me 5. Is 0 less than 5? It is. So that tells me that this point works for this equation. And any point on this side of the line will also work. So you could pick really any of those points. You could have picked this point right here, which is 3, negative 5. And 3, negative 5 should give you a correct answer. But if you picked a point up here, like this one, at 0, what is this, 5, 6, 7, 8. 0, 8 should give you an incorrect solution. You can try it out. Is 0 less than, not 0, but is 8 less than 5? No, it's not when you put that in there. So that means that this side doesn't get shaded. So just to kind of sum that up, you graph it like you normally would a line. If it's no bar underneath, you make it a dashed line. That means you don't include points on this as your solution. None of those work. And then you pick a test point that's not on that line. So I picked a test point 0, 0. And if it's a true statement that you get, you shade that side. If it's not a true statement, you shade the other side. Let's try another one. Try that one out. So for this one, I'm going to graph it like I do any other line. I say, okay, my y-intercept is negative 1. The slope is 3/4, so I go up 3 and run 4, or down 3 and run 4 this way. And then since there's a bar underneath, I'm going to use a solid line this time to draw a line. That means that all of these points on this line should be a true statement when I put it in there. But now I need to shade a region. Is it going to be above the line or below it? So I'm going to use the test point 0, 0. So putting 0, 0 into this, I get 0 is greater than or equal to 0 plus negative 1. So 0 is greater than or equal to negative 1. That's a true statement. So everything over here gets shaded. That means all those points will make a true statement right there, including the ones on the line. Try this one out. So for this one, before you can start to graph it, we need to get y by itself. So I subtract 3 from both sides. And subtracting 3 from the 5, I get plus 2. I'm going to graph the line like I normally do. So I go up to, there's my y-intercept, and the slope is fall 3, run 2. And because there's no bar underneath, I'm going to use that dashed line to say we don't include those parts on there. And then put in my test point 0, 0. So putting in the test point 0, 0, you should be able to do it on either one here. You can do it up top or down below. I'll just use this one, and I get 0 is greater than 2. Is 0 greater than 2? No, it's not. So that means I don't include this side of my shading. I want to shade this side right here. So if you picked another test point, you could. You don't have to, but if you pick something like 2, 2, that should work. So put in 2, 2. You get 2 is greater than negative 3 plus 2, which means 2 is greater than negative 1, which is a true statement. So any of these points should give you a true statement when you plug them back in. Try out this one. So this one, if I put it in slope-intercept form, I got to get y by itself again. So I add 1 to both sides. So I get negative 2 is greater than or equal to 5 halves x plus 2. And then I need to, or it should be a y there, I need to divide both sides by negative 2. Now remember that anytime you multiply or divide both sides by a negative with inequalities, you have to flip the inequality. So here I'm dividing by negative 2, or you could say multiplying by a negative 1/2 if you want to, but I must flip that sign when I do it. So it goes from greater than to less than or equal to. So this becomes a negative 5x plus, actually it's going to switch to a negative 1 here. And just to show you, because sometimes students I know in class are like, where did you do all that? All I'm doing here is multiplying both sides by a negative 1/2. So when I multiply this, I get a positive 1. Basically cancels, for lack of better words. And then I need to distribute this to both sides here. So negative 1/2 times 5 halves, the 2's. Actually, see, it's a good thing I checked my work here. This becomes negative 5/4. And then a negative 1/2 times 2 gives me negative 1. So that's good that I work a little bit slower there. Keeps me from making mistakes. So now I need to graph this. So graphing it, I'm going to go to negative 1 and plot the point. That's my y-intercept. And then this tells me to fall 5 and run 4. So 2, 4, 5, run 4. 2, 4, 5, and run 4 this way. 2, 4. There's a bar here, so I need to make sure I have a solid line picked. Draw it right through there. And then I need to figure out which side to shade. So remember, you got to flip this inequality here or you'll get it wrong. That's only because I multiplied both sides by a negative number. Anytime you multiply or divide by a negative number, you got to flip it. I'm going to pick the test point 0, 0 again since my line doesn't go through it. And I get 0 is less than or equal to negative 1. Is that a true statement? It's not. 0 is bigger than negative 1, so I need to shade this side of the line. Make sure we get arrows on the end here. All right, so that wraps up in a very quick sense graphing inequalities and graphing or linear inequalities and graphing linear equations. The next thing we're going to talk about is systems of inequalities and systems of equations. Now, before we talk about systems of equations, I want to emphasize a few points about just basic linear equations, or really just any type of equation in general. When I give you in some type of format like this, we've already discussed that this 3/5 right here is the slope, and that the 2 is the y-intercept. But we really didn't say what does the x and the y mean. So what the x and the y mean is they're any point that's on the line. Or another way to say it is it's a solution to that equation. So let's go back and graph this line again. The y-intercept is 2 and the slope is 3/5. So you run 3 and you rise 3 and you run 5. And you draw a line in all those points there. Now, the x and the y stand for the solution to that, or in other words, any point that's on the graph. So with that being graphed, if it's graphed accurately, you should be able to look along this line and pick a point. Let's pick the point like this one right here. It looks like it crosses there. It might be a little bit off because sometimes it's a little inaccurate. 1, 2, 3, 4, 5, 6, 7. So my x value is 7, and we go up 1, 2, 3, 4, 5, 6. Now, like I said, these lines are kind of clunky when you're drawing it on the computer, so it may not quite be at 7, 6, but let's test it out. If I take 3 times 7, I get 21 over 5, plus 2, does that equal 6? So 21 divided by 5 is like 4.2, and 4.2 plus 2 gives me 6.2, which does not equal 6. So this point is not really on the line. All right, if it were on the line, you would get something like 6 equals 6 there. So, and like I said, it's mainly because I'm just kind of looking at, an imperfect situation here where I'm trying to draw and the line's very thick and it looks like it goes through those crosshairs. But in general, any point you pick, like 0, 2, should work. If I put 0, 2 into this equation, let's see, I get 2 right here equals 3/5 times 0 plus 2. This goes away, so you get 2 equals 2, so we know that point is most definitely on the line. But in general, if I have an x and a y there, any point that's on this line, if you want to test it out, is it really on the line? You can put it into this equation and it should give you a true statement. If it doesn't, then it's not really a solution or it's not really on that graph. Now, that being said, let's go look at this right here. This is what we call a systems of equations, meaning we have more than one equation. And what I really want to know here is, what's a point that will work for both of these? So, or in other words, what's a point that's on both of these lines? So let's graph both lines. The first one here is -1, so let's put in a point at -1, and the slope is -1, run 4, or rise 1, run 4 this way. And draw a line. Oops, let's go back there. My computer's lagging, so it's not. Try to draw this a little bit slower. Let's see if I can fix it. All right, so there's our first line. The next one is going to be y equals 3. So y equals 3 is a horizontal line at 3. And so at their intersection is the solution. So this point right here is the only point that's on both of these lines. And so if you put this, it's the only spot where it will work for both of them. And when you learn this in Algebra 1, you learn that there were 3 different ways to solve a systems of equations. You could solve graphically, which is what I'm showing you right now. You could solve by substitution. And you could solve by elimination. So today we're mainly focusing on the graphical explanation because I really want you to understand what does it mean graphically. And so if this graph continued on forever, we could actually just count how far over and how far up we go to get that point that works for both. But since it doesn't, I'm going to show you substitution real fast. Substitution means if you get one variable by itself, which this problem has already given me, you can substitute it into the other equation and solve for the unknown variable. So if I do that, I get 3 is equal to -1/4 x minus 1. Add 1 to both sides. Multiply both sides by -4, and you get x equals -16. So this point right here is at -16, comma, +3. And that's a point that is on both of these lines, so we say it is the solution to these systems of equations. Now, there are times when we don't have any solutions, like if we're drawing lines here, where the lines intersect is the solution to the 2 lines, so that has one solution. Sometimes the lines are parallel though. So if the lines are parallel, if they never intersect, then we say there are no solutions in that situation. And then sometimes you get lines that are not parallel. They have the same slope, but they actually lie right on top of each other. And so if you draw the same two lines and they land right on top of each other, they intersect everywhere. So since lines go on forever, there are infinitely many solutions. So sometimes you see that. In general, if you get a non-true statement, when you're solving these equations, sometimes, graphically looking, you can quickly see one solution, no solutions, infinitely many when you're graphing them. But if you're solving them using substitution or elimination, then you'll see instead of getting a value like this, you'll get two numbers, like the x's will cancel out somehow. So if it says something like negative 16 equals negative 16, a true statement, then you know there are infinitely many solutions. And if it says something not true, like negative 16 equals 5, then there are no solutions. We really won't worry about that until we talk about, if we talk about substitution and elimination. Like I said, today we're just looking at the graphical explanations, and those kind of take care of themselves. You can kind of see intersect in one spot, one solution, no spots, no solutions everywhere, so it's infinitely many solutions. Try this one out. Graph these two and tell me what the solution is. So graphing them, we're going to go to positive 2. The slope is 3/5. Draw your line. Graph the other one. So here, 1 is right there. The slope is negative 1/5. Draw your line. And if I had to guess here, I would say the solution is negative 1, negative 1. Now that may not be true. We can check that in a moment. But if I was on a quiz or a test and I asked you to find the solution graphically, I would accept that. So long as you could show me that you graphed both lines accurately, you might want to label which line is which here, so I know you graphed it, fully. I would take negative 1, negative 1, or anything close to that spot right there as a solution. If we wanted to check it, you could put it in and say, does negative 1, if I put negative 1, sorry, not negative 1, negative 1, negative 1, positive 1, if I put positive 1 right here and negative 1 in, do I get a true statement? So it doesn't look like it. Let's see here, we get negative 3/5 plus 2 equals negative 1. This is the same thing as 10 over 5, so you end up with negative 3/5 plus 10/5. Does that equal negative 1? Why do I keep saying negative 1? Positive 1. And you get 7/5, which is like 1 2/5. So no, negative 1, 1 is not on that line, but it's really close and it's hard to tell. This is the problem with solving them graphically, is sometimes they don't, and it's not very easy to tell, and you have to use a different method. But I would accept that if you were solving it graphically on a quiz or a test. Now we can also have inequalities have systems. So before, when we graphed an inequality and said shade this side, we meant that any xy point you pick in here, or if it's a solid line, any point on the line will work for the equation you're talking about. That's why we did a test point, to see if, if we test it 0, 0, if it works, all the buddies around it will also work. If it doesn't work, none of these on this side are going to work, and they're all the solutions are up here. So we're going to do the same thing with this, but when you have two, you want the intersection of the solution points. So let's graph these two. I'll graph the first one. I'll pause it to graph it for you. So the first one graphed looks like this. I did the dashed line because there's no bar underneath. That is it graphed correctly. And then I tested 0, 0. It gave me a non-true statement, so I shade the side above it. And now I'm going to graph this one. So let me do that. So when I graph this inequality, I get this red line right here. It's solid because it has a bar underneath it. I tested point 0, 0 again, and once again it was not true, so I had to shade the other side. Now for the complete answers, what I want are points that will work on both of these. That's the systems part of it. So when I look at this, where do the two overlap? And they overlap right here. If I shade it this more green, you'd see it all shaded with green, and this is all red. And so this is my solution. I want to darken that in well enough so the teacher knows That's what I'm saying the answer is. If you're doing this with pencil, always shade this lightly, and then darken this in right here. Remember, this is still a dashed line. This is a solid line, but all of these points inside of here will work for both of these and give me true statements. Let's try one more. Try out this one right here. So this is actually the first one like we did in the last one, where we have above the dashed lines there. And then y is less than 3. So graph out y is less than 3. Where y being equal to 3 is anywhere in here that's like this. But wait a minute, there is no bar there, so I need to make this a dashed line. Let's go ahead and do that. Boom, there it's dashed now. And test out a point 0, 0. Will 0 work? Is 0 less than 3? It is, so that means shade below it, like this. And so my solution is going to be the intersection of the two shadings, which is going to be anywhere in here like this. All right. So I know we went through a lot. We went from just plotting a point to graphing a line, graphing an inequality, graphing systems of equations, and then graphing systems of linear inequalities. If you have any questions, let me know. I'll be happy to go through any of the examples or all of them with you individually. But if it is just a review for you, maybe you have a good strong math background, go ahead and do the homework, give it a try. And for any of you, let me know if you have any questions. Thanks for watching, and I hope you're having an awesome day.